Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about Helion nuclear fusion reactor design and whatever. Let's dive right into it. So what exactly we are talking about here? We are talking about a magneto inertial fusion system. Wait a minute. Those two things are kind of different. Well, yes, they are. Like recently, we had a news about that inertial confinement system finally achieved break even, meaning we put 2 in, we got 3 out. Awesome. Now, his deal back in the few days ago, even in terms of basically magneto plasma system, we also had the same output, whereas we put few megajoules in, we got few more megajoules out. That happened. So we have achieved break even in both of them. Now, here's the problem with both of the system. A laser system that is powerful enough to achieve inertia high enough where it's like, no, I'm gonna achieve fusion, that puppy is expensive, meaning idiotically super expensive, meaning nobody would ever build it unless you are USA and unless you are like literally trying to develop a nuclear weapons protocol rather than fusion system. Like nuclear weapons protocol is so expensive that it's like, yeah, worth it. And side outcome was like, okay, fusion system. And magneto system, again, tokamaks and ITAR reactors, those are idiotically expensive. So the idea is, if you marry both of them together, the price will come down. Like, wait a minute, that should trigger a red alert. It's like, how the heck mixing two super expensive technology would make it cheap? Well, here's the deal. Price of things go exponentially based on demands, meaning if you want a generator that is 1 megawatt, that's okay, expensive is okay. 10 megawatt, bit expensive. 100 megawatt, now we are talking. 1000 megawatt, idiotically expensive. The price will not go up by like a factor of 10 or 100, it will go up by 1000. Price starts to go up. Same goes with magnets. When you are going to someone and asking, bro, I want an electromagnet that is, let's say, powerful of 1 Tesla. They're like, okay, we see you. It's an old MRI magnet, 1.5 Tesla. Price goes up. Now, once you start to cross, let's say, 10 Tesla, they're like, yeah, bro, write a blank check. Don't ask price, just write a blank check. And there lies the problem. If somehow you can tone both of these two things, obviously, inertial systems and a magnetic confinement system, low enough where they are no longer using components that are idiotically expensive, they're like, price will come down, even though you have two systems. So that's the whole point. Basically, two easy systems, easygoing materials helping each other out. So what is the use of the magneto part of it? Well, it's a magnetic trap, meaning you take a gas. Basically, this gas is this puppy. It has the thing that you want to achieve fusion. Okay, cool. Now here's the, generally a gas is neutral state. It's like chill. We're not gonna do anything. You pull a vacuum in the chamber and you inject the gas. Now here's the deal. The gas has to get energized. Insanely high amount of energy. Either you dump it with a radio frequency or you dump with a microwave. Whatever you do, you dump GG amounts of energy into it. Now once you dump the energy, it makes it unstable, meaning it strips the electron out of the nucleus. Basically, atoms. It's like two different parts. Now, here's the deal. Both of them parts are charged. Why? Because neutron has no charge, but it's bounded together by protons. Protons are like, I'm positive. Negative. Neutrons, electrons are like, I'm negative. Now, here's the deal. Both of them have something, meaning both of them have charge at this point in time. Now your neutral gas is behaving like a system that will react to magnets, and there comes the magnetic trap, meaning using magnetic power, you can lock them up, you can cycle them up. Basically, you can create a donut or do whatever the heck you want to do with it. You can act on it using magneto side of it. Okay, awesome. You got the point. Now here's the deal. Doing this is easy. Achieving fusion condition only using magnet, the magnet price goes YOLO. Here it does not. It's like all you are doing is dumping energy into the system, making it super hot, basically creating ionized system, and then isolating it from chamber walls, because if it touches chamber wall, it will dump all its energy, it will cool down instantaneously. So you got it, that magnetic trap system. Okay, now inertial collision starts to happen. Now basically you inject this particle from left side and right side. Basically they are symmetric to each other. You go boom like this. Now that's the another part of inertial system. Basically, using the magnet itself, you are creating an accelerator, a sort of linear accelerator that are working towards each other. Now at this point in time, you can achieve very high speed. How much high speed? 300 kilometer per second, like ludicrously high speed. And then you squeeze this puppy using electromagnet, basically sequencing it. Now some energy you got from heating the plasma, another energy you got in trapping the plasma into one twizzle and heating it up, another is inertia. When you are colliding these two things, they are traveling at 300 kilometer and both are symmetric, meaning X amount of energy is here, X amount of energy is here. Once they collide, they cannot go each other, they cannot like push each other. Like what the hell, that will happen? That heats this puppy up insanely high. Now if you wanted to achieve this sort of insanely high temperature using lasers, laser would be stupid expensive, magnet super expensive. But here you are using inertia, you can achieve this very effectively, meaning without using idiotically expensive parts. And when you achieve fusion, basically you charge the particles up, you heat them up, then you smack them, smacking that particle, and then again, of course, you will have final compression also to put some extra love into the system. So then you achieve fusion. So that's the whole point. That's why there are two terms in this, magneto and inertia. Basically, you are taking magnets like, bro, I don't need the latest and greatest magnet, just get this thing done, and then you accelerate it. You utilize the benefit of delta V, and then they go. And then when this is happening, you have to understand the delta V between them is around 600 kilometers per second, very fast. And what they're gonna use in terms of fuel is deuterium helium-3. Now you are like, wait a minute, I heard helium-3. Well, I'll explain that further, but you have to understand that the reason why they want to use deuterium and helium-3 is that when they are compressing the final compression, it's going to create fusion. Now here's the deal. If it's aneutronic in nature, it's going to push out protons. Now protons is going to carry majority of the energy. In normal fission reaction and normal fusion reaction, you get a neutron out of it. Now neutron is chill guy. Neutron does not care. You have the greatest magnetic shield. It's like, I do not care. It just goes through it. Now that's how tokamak works. Neutron crosses the magnetic bottle, touches the wall. Wall generally has water running through it to cool it, and then the heat, the thermal energy of that neutron is captured by water, and water heats up. Then you run a turbine. Here, because you use magnetic compression, that magnet rebounds because you are getting protons, not neutrons. That's why aneutronic fusion is important. That's why if you keep hearing things are, we're gonna mine the moon, that's what they are talking about, helium-3. The reason why helium-3 is so interesting is simply because you do not have a basically steam cycle, no thermal cycle. You do not even need supercritical CO2. It's just like the very thing that is creating the plasma, creating the fusion, is the very thing that's gonna react against the byproducts of it and then bounce back. Now that will create, like, you will create a sinusoid that is going like this. Fusion happens, fusion dumps the energy into the system, you get positive energy that you sell into the grid, again you collapses using the energy of the capacitor. So this is direct pulse power production. That's why they keep using the term generator, world's first generator. That's the idea behind it. That's why they do not have a steam system, because they are using a neutronic system rather than using normal neutronic reactor. Neutronic reactor will require 50% wastage simply because of converting thermal energy into electrical energy or any sort of useful energy, which again 50% is a bit optimistic. Realistically, you'll get 35%. So that's what we are talking about here. That's what you see in this video and all the viral jazz. So when this is going to happen, because I'm pretty sure this is one thing you have to understand. If somebody says, I achieved fusion, that's child's play. And I do not mean this like a joke. I mean this literally. Like Google, who is the youngest person to achieve fusion? Yeah, actual child, like 12, 13-year-old child, actual. So achieving fusion is child's play. Achieving break-even fusion, that's a bit difficult. But achieving break in a factor where it's like, yeah, I dumped 2 megajoule in, I got 2000 out. That's what we want. We put, because all we have to do is pump fuel in, voila. That we never achieved. Even in the laser system, we put 2 megajoule in, we got 3 megajoule. Is that useful? No, 100% useless, because the laser itself is so inefficient. And after you convert, add into the factor of like basically plug power to the actual power, yeah, not happening. So you have to understand, we need factor of 200, hundreds. Anybody is talking like in percentage, not good enough. It has to be multiples, and it has to be big multiples. It cannot be tiny multiples like, yeah, 3 multiplied by 3. No, it has to be big multiple. Has to be in triple digits. That's the part that we never achieved. Everything before that, basically achieving that high factor, we have achieved everything. We have just not achieved a point where they're like fuel in, power out. We just have never achieved it. All we have is like fuel in, poof, that's it. We never like just keep adding more fuel, like how your car engine works. Like you add more fuel, it gets more boom boom. That does not happen here. So that's why they are not even close to break even. And here's the deal. Why the heck you have never heard of this sort of system where somebody is actually trying aneutronic nuclear fusion if it's so amazing? And if you're like science fiction nerd, that's why Tony Stark's shield, basically arc reactor works. It's an aneutronic system. If I have to be scientific about it, it has to be proton-boron reaction, because be mindful, while the primary output is only proton, it will interact with things around it and some byproducts. It is going to create secondary radiation. Not the primary. Primary radiation won't be there, but secondary would be there. But if you use proton-boron, you will not have any radiation, even in secondary. Everything will be proton, proton, proton. So you're going to have GG power. That's what Iron Man uses. Now, why the heck nobody tries this if this is so amazing? Why the heck we only hear it in science fiction and people talking about moon mining? Well, reality is harder. Like how much harder? Well, here's the graph that you can see. We have deuterium and tritium. Now, this puppy requires some oomph. That is 13.6 kilo electron volts oomph. Like that's some serious oomph that it needs to do the job. Now this is the plot graph. They're basically reactivity and temperature required. Now deuterium tritium is the blue line. Okay, easy. That's why everybody's trying that. That's the easiest that we have found in entirety of periodic table, entirety of isotopes available. That's the easiest. That's why every Tom, Dick and Harry is working on this. Now what happens if you go to deuterium helium? That jumps to 58. Yes, you can directly convert the energy output from basically nuclear reaction to electrical power, but achieving the ignition is very, very difficult, and exponentially achieving break even is even more expensive. That's why nobody is even trying this. Like nobody serious is like, yeah, I'm gonna do proton helium reaction. It's like proton, sorry, deuterium helium 3 reaction. It's not useful because it has the, if you can just do it, you can just do proton lithium. That requires 66. Or again, proton boron, that's amazing because it has 0 secondary radiation. But you can see the reactivity, like it starts at much higher temperature. It's like before, by the time of normal tokamak is like, I'm producing power, this puppy is like, I'm not even start. And here's the, if you can actually achieve a reactor that works at this deuterium tritium, you no longer need deuterium helium 3. Yeah, you have to waste, let's say, 70% of energy. Here's the deal, pump more fuel in. We have a lot of deuterium and tritium also. Yes, tritium requires breeding, but it can be managed. If you can just burn more fuel, we have it. It's sorted. And that's why there is another circuit also, that is deuterium tritium. It's a bit more green line basically, but again, still easier than helium 3. That's why nobody even tries to do this. We have helium 3. Now another aspect is like, oh, helium 3 is not here, that's why we do not do it. Yeah, we have it, helium 3. That's how we figured out that's how much energy it takes. We have it. Do we use it? Yeah. If you ever seen this sort of image, there's a very good chance it has helium 3 in it. That's how we achieve almost absolute zero cooling. Like if you ever typed absolute zero cooling, that's what we use, helium 3. Now, of course, it's not absolute zero. It's like nano Kelvin or something like that. That's why, like, fundamentally, if we have the technology to achieve this, we no longer need this technology, because you can just achieve deuterium tritium and you have plentiful fuel, you have plenty of breeding reaction, and it's like, bro, I don't even care. Or maybe you're just like, I don't even like breeding reaction, just go with, like, you know, deuterium cycle. That's super easier. We don't do it because, again, if we are pooping ourselves at 13.6, how the heck you expect us to do anything at basically 58? That's the whole thing. And here's the deal. Helion Energy startup. Fourth nuclear fusion prototype, planned path to a commercial 50 megawatt. They are damn sure about the break-even factor at this point. 50 megawatt pilot nuclear fusion reactor in 2019. I'm pretty sure this is beyond 2019 at this point in time, and be mindful, this happened on October 29, 2013. That's why I'm not even interested in this sort of thing. It's like, have we achieved fusion? Yeah, it's child's play. Have we achieved break even? Yeah, both of the system, inertial confinement system and plasma system, both have achieved it. It's just that factor we need, like we need factor of hundreds. What we have is percentage. We are like off by a long mile. And like this sort of like just investor thing is like, you know, we just say something that we take the money, then we create some videos and we get more hype, more investment money. Then it's like, we keep pushing the deadlines. It's like, bro, there is a reason why every Tom, Dick and Harry is trying deuterium tritium, is because it's the most likely that it's going to work. Deuterium helium, and again, be mindful, even though the aneutronic part sounds good, it's not like you do not have to worry about radiation or idiotically large capacitors. That's the whole thing. That's why nobody even tries to, like, if you are failing, it's like if you're failing in board exam and you're directly trying to achieve, go for, let's say, medical exams. It's like, bro, clear the board exam first. Same thing here. It's like, that's why it's the when part is the most important. We have achieved fusion. It's like, yeah, children achieve that. We achieved break even. What is the factor? Is it in multiples? Let's talk. If it's not in multiple, shut up. So what is the cost of this sort of system? Because here's the, at the end of the day, I specify 3 things. You have physics. Is the physics gonna say yes or no? Then we have engineering. Can we actually make it? Because again, physics says we cannot go faster than light. Okay, that's good, that's fine. What about engineering? Can we go till light speed? Hell no, engineering is like, bro, 0.10 C, enjoy. Like 10% of light speed, that's more than good enough. And then we come to economics. Can we actually build it? No. Into economics will be like, dude, 0.0001 C. That's all you're gonna get. Economics, that's the final layer. If it does not work economically, it's not gonna happen. So how do we measure the economic part of it? We measure the economic part of any power plant. It does not matter, the coal, geothermal, whatever heck you. It's dollar per kilowatt hour, meaning 1 unit of electricity. How much dollars I have to put down for 1 unit of electricity? That's the key factor. Everything else is meaningless. So solar has reached, again, be mindful, this number goes up and down a little depending on the situation, depending on the inflation, but generally it's 0.075 cents kilowatt hour, 1 unit of electricity. Wind goes even lower, that is 0.005, basically almost 5 cents or even 2 cents in some scenarios for 1 unit of electricity. And we bitch about these things are expensive. And be mindful, and nowadays you will keep hearing things like coal has finally been surpassed by solar. The reason is coal is crossed this threshold. Why? Again, coal supplies is dwindling. All the open pit mines, again, there was a limited amount of coal. Once you start to see that, hey bro, we are at the last leg, you increase the price. In consequence, electricity price goes up. So fundamentally, solar is becoming the thing. The reason why, even though wind is cheaper, nobody uses it, is the capital requirement is brutal. It's like bit expensive capital wise. But again, be mindful, these two technologies are here, they are real. We have sorted majority of their problems, and we are at the final stage of their deployments. And we are bitching that they are expensive. Now, how do you know something is going to be expensive or something is going to be cheap? One thing you have to understand, the complexity of the tool that you're talking about. For people who are familiar with computers, they are familiar with the fact that hard drives, no matter how low capacity they are, they never go down below a certain price. While SSDs, they can go even lower. How the heck that happens? Well, reality is SSD is just a PCB with some flash chip on it. That's super simple mechanism. Basically, you have a PCB board manufacturing system, and then you have chip laying, basically pick and place machine, and voila, done, go home. What happens in a hard drive? You have same, basically, it also has PCB, okay. And then you have a metal chassis, that is very expensive, okay. Then you have a motors, that is spinning a platter, okay, you added cost. Now you have actuator that moves. Now you added a lot of cost. That's why the hard drive prices never go down below a certain point, while SSD can go below a certain point. Why? Complexity. Complexity has a physical limitation. It does not matter whether you are making 1 copy of it or billion copy of it. If complexity is too goddamn high, you will never be able to drop price beyond a certain point. There is always a limit. Like for example, a car. Like a car can never be as cheap as a mobile phone. Why? We have been manufacturing for so long. Again, it has too many parts, too many steps, too much complexity. And there lies the tool part of it. Even with modern technology, even though, oh, we're going to make hundreds of it and it's going to be cheap. No, if the complexity is too high, fundamentally it cannot go below a certain point. Then we come to the driver aspect of it, meaning the people part of it, the skill set. If it needs skilled people, its price is going to be very expensive, no matter when you are going to do it. For example, a watch, like luxury watches. Even though nowadays they are being built by CNC machines, they are still idiotically expensive. Why? Skill set needed. The people who can understand the damn thing is very few, and people will only work if they know that they're gonna grow from it. It's like, hey, I started for $100, now I work for $120, now I work for $120, otherwise why the hell I am working? So that's the whole point. Skill price also goes up. So even a fusion power plant, even though the technology is kind of dumb, people driving it is very complex people, because they have to understand the isotope parts of it. Because if a normal person, you go to a reactor and it's like, bro, why the heck is showing xenon poisoning? Who put xenon there? They're like, dude, xenon is the byproduct of half-life decay of some element isotopes. It's like, it's a complicated thing. You have to be good enough to understand it. What the hell is happening here? So price goes up. Nuclear, that's why nuclear never goes beyond a certain point. It's like the people needed to do that is expensive. Nuclear fusion, yeah, it's going to be expensive. So these two factors combined guarantees no matter what you do, you will never be able to go below a certain point. Now here's the deal. Why the heck solar went so low? Well, reality is solar was riding on the success of silicon technology. Whereas like silicon, everybody is working their ass off to make basically smaller chips, more efficient chips. We are like, okay, what if we just nudge it, like, just same technology, awesome. Then also electronics industry was also moving there. Now we have inverters that are super cheap. So these two technology allowed solar to become so cheap. Wind, inherently simple technology. We just figured out, hey, composite structures, we have been making them for long, from F1 and all that jazz. We have been doing that puppy for years. What if we just keep it making bigger? Is that inherently simple structure? Is just lay it, cook it, lay it, cook it, lay it, cook it. We keep starting to make it bigger. Of course, within limit, but price started to come down. Would this happen to fusion? No. No, just opening your mouth and saying that I need a magnet that is 10 Tesla or 9 Tesla, that's the world's most expensive MRI kind of level thing. Like, that's why even majority of MRIs are still at 1.5 Tesla. That's the whole thing. Cost cannot go below a certain point if you have too high complexity. And then we come to the, like, how long these things are. We do build complex things if they last forever. Basically, if you build a good quality coal power plant, you actually don't have to decommission it, because if it's running properly, it will just keep running. Like, we have actual steam turbines that have been running for 50 years. We have turbo generators that have been running for that long. Like, it's a known thing. Of course, we do refurbish them every 10 years, but it's a thing. Like, we know how to do it. Can you do that with something that is this high energy density and radiation? Because yes, proton majority of energy is there, but other radiations will be there. So fundamentally, longevity of this sort of technology is just not there. So fusion tech, no matter what way you slice it, no matter how you do the math, it will never come out too cheap. And if you are bitching about solar and wind, fusion is going to be the same thing. It's like, yeah, this power source works 24 into 7. Just nobody can afford the electricity that it makes. What's the point? It's the same thing. That's why don't go into that, oh, it's 24 into 7. Dude, would you pay for electricity if it's 10 times more expensive than today's? No, you're like, bro, me good, bro, me good. Same thing. And then we come to the reason why I'm so fed up with this sort of thing. It's the urgency. Like, I have an urgency in my heart where it's like, dude, this is serious. Like, global warming is getting serious point. Now, many people are like, I don't believe it. I don't care. It's like, you cannot believe it. It's like, to those people, to like communicate to them, I just use economics. It's like, hey, coal power plant, expensive. Solar power plant, cheap. That's how I communicate to people who are like, you know, renewables are cheaper. Like, in long run is always cheaper than any sort of fossil system. So fundamentally, I have to ask you this one question. How long do you think before we start to reach a point where crop yield starts to go down? Crop yields meaning we plant a crop and nature is like, nope, basically it's too goddamn hot, like droughts that happened recently as in like 2022. Basically, at what point do you think this will become a severe enough where food output will start to get, because that's where everybody gets affected. That's the point where your money does not protect you anymore. That's a brutal point. That's the breaking point. Everything, like, yes, it is true, Earth can go as bad as Venus, but yes, we will be long dead before that. So that's not an issue. Let's be real. What affects you and me? Crop yields, meaning that if the moment crop yields go to red, basically we are no longer getting able to farm crops because soil temperature is too goddamn high, sun is too brutal. It's just, there is not enough water source because majority of glaciers have dried up, rivers just have flash flooding nowadays, and voila, everything else is a sewage water. How long do you think that has? Like, again, for many people, it's 30 years. I'm taking that 30 years because I'm seeing rivers. Like, rivers are a common thing in India. I'm seeing rivers drying up exponentially, meaning I can count basically how many rivers are alive now. Even though we used to have hundreds of major rivers, multiple of thousands of small rivers, now majority of them are dry majority of the time. So how long do you think we have before that food supply starts to become, yeah, we no longer have that safety? That's the point. Now, why the heck we are falling for this then? It's like, I cannot be the only wise one. Well, here's the deal. Human psychology does have an inherent limitation. Whenever we are confronted with big problems, we like one magic bullet solution. That's a human psychology. It happens to you, me, every Tom, Dick and Harry. This is one important aspect of it. Basically, if it's like, oh, your life is a mess, do this, it will sort you. No, it will never happen like that. You have to like, okay, now I have to solve my discipline. Now I have to fix my food habit. Now I have to do this. Like, people are like, what if I would just become more disciplined? No, sir, you are eating bad. You have to fix that also. What if I do? No, sir, you have to be in good habits. You have to be in good circles. Everything you have to fix. Then we are not used to that. We like, dude, give me this magic pill, solves all of that. Like one magic bullet. That's why we are stuck in this loop where it's like, rather than utilizing tools that we have right now that works, we are seeking for this magical tool. So if we have all the tools, if we use them concurrently, they will fix today. Meaning, if we start deploying them at mass today, next 30 years from now, we would have slowed down carbon output to such a point where it's like, okay, stop. At that point in time, we'll make a decision whether we want to sequester it or just like let nature sort it out over 100 years or 200 years, and voila, problem would be sorted. And then we can utilize even better technology if we need to. But here's what are these current technologies that I'm talking about? Well, we have solar, we have wind, we have biogas, we have seaweed. Seaweed simply because people are like, how the heck are we going to fly jet fuel? It's like seaweed biofuel. You do not even need to modify jet engine. This is one common misconception. It's like many times people confuse biofuel with bad biofuel. It's like biofuel, if done correctly, is a fuel. It's hydrocarbon, meaning your engine will not be able to tell difference. The reason why people conflate too is like many times biofuels are alcohol group, not hydrocarbon group, like ethanol, methanol. Those things are low-grade fuel compared to petrol and diesel, simply because while they have oxygen, they burn cleanly, they do not have the oomph. So if you directly want to use, let's say, a fighter jet on ethanol, it's going to burn very cleanly. That's awesome, but it's not going to have enough oomph to that. So for that reason, if you create basically seaweed biofuel, you create RP1 out of it or JP1 out of it, you're going to run it into a basically jet system and it's going to be fine. How do I know? It has been tried from like 2005. Like Pentagon tried it on fighter jet, and now many passenger jets, you can see that there is a stamp on the jet engine is like biofuel. That's what they are using. It's a known sorted technology. Then you're like, how about energy storage? Closed loop pumped hydro. Again, all of these systems, none of them are perfect. But if you deploy all of them, it solves each other's problem. Then you're like, how the heck you connect so much energy so much far? HVDC. Of course, AC link does not go that far, but HVDC does. We have links that are 3,000 years, 3,000 kilometers long. At that point in time, you're jumping continents, like Australia to UK or somewhere. You can do that. So that's why urgency is important for me. It's like, that's why I hate this sort of like magical in future. No. Today, fix today before we end up in a red. Not only urgency, there is also an aspect of penalty, meaning inaction is gonna cost us a lot. For example, if you waste money and time, those are limited resource, meaning you cannot just print more money and you cannot just create more time. Time definitely, money maybe, time definitely. So that creates a scenario where, for example, like Indian has states, like one of the very popular place was Mumbai. It wasted money on Hyperloop, which every Tom, Dick and Harry that does holistic system analysis or specifically works in transport, they were like, dude, this is not gonna work. This makes white elephant projects look good. That's how bad it was. And government burned millions, hundreds of crores on it. And what happened after that? That money, poof, gone in the wind. What about the time? Like years have been spent on like actually building that system, gone. Like again, if that much money would have been spent for, let's say, literal basic things, for example, metro, that is above grade metro, like a viaduct kind of metro, we could have reached connected two places. Again, it would have been not as flashy, not as sexy, but it would have worked. It would have saved CO2 emissions today. But we don't have it. We have nothing. We just have debt. That's why these things are limited resource. We cannot just like, what if this? No. We don't have that kind of luxury anymore. Another aspect is when you create this sort of hype technology where it's like, do this, it will solve all the problem. Like exactly how people were talking about, like, we're going to have Aneutronic nuclear reactor. It's like, dude, we are having a hard time with deuterium, tritium. You're just going to talk about like, we're just going to have fusion. It's like with helium. It's like, dude, the break-even factor on that will be idiotically more complex. So that creates an illusion for many people where it's like, I'm not gonna blame them. It's like many people will be like, hey, I don't have to do any action. I don't have to change my lifestyle. I don't have to do this. I don't have to do that. It's like, they're gonna sort it. But here's the deal. That sort of hope is very risky. And that's why we are in such a mess right now. Like majority of our problem would have been sorted by now if we had just listened to the old guards. We just literally hoped for a better technology that never came. We have a history of this. So if we force working tools at this point in time, all the main tools that I talked about, literally we will have a better future. We will have a future where everybody's like, bro, we don't have to worry about natural gas, we don't have to worry about crude oil, simply because we got everything we need. Like right now, yes, it would be expensive, but it would be direct result is like, yeah, so instead of burning billions of dollars on carbon capture, burn billions of dollars on trillions of dollars on nuclear fusion, we'll have plants where like, okay, we are working, okay, we have a carbon neutral jet fuel, okay, we have a freaking wind system that actually works, okay, we have HVDC links that work, it's like connecting power far away places. All those things will work today. We'll literally start to reduce Earth's carbon footprint brick by brick, day by day. We'll start to move rather than just like, let me wait. Well, let's see the future. It's like, bro, what if CO2 reaches a critical point, tipping point? Once we start have crop failures, who the hell is gonna pay for like this magical technology? And here's the who? Like at that point in time, who cares for that? It's like nobody cares at that point in time. Once you are hungry, you don't care about anything else. So fundamentally, if we like work together and use working tools today, we'll have a future. Then we can sort it out. Like once we have all the taken care of like CO2 emissions, then you're like, okay, then replace it with a fusion system once we sort it out. Right now, that's not a good option. Because you have to understand, society must be prosperous for anybody to give a damn. If it's not prosperous, nobody's gonna give a damn. Like for example, this is a US lake that just lulled it. This is China's river. It's like that's how quickly water is evaporating that fishes are not able to move away from it. That's a whole river. This happened in 2022. Like this is Italy's scenario where it's like majority of crops are like poof out of existence, and the drought that they are having is brutal. Same happened with France also. There's like we have nuclear power, we don't have to worry. It's like, and rivers are like, nope. You don't have a nuclear power plant, you have something that looks like a nuclear power plant, which I cool, because if I don't cool it, you have to shut down your reactors. That happened. Not even making that up, that actually happened. They were that serious. Is like, if we dump so much hot water into the rivers, it's actually gonna disappear. So they had to like throttle the power output. I'm not even making that happened in this year. So there is penalty of like waiting for this sort of fusion technology, waiting for this and that, rather than utilizing the tools that we have today that will reduce carbon footprint today. Like there's penalty for that. It's not just like lol. There's a penalty for that. Like expensive penalty. Like yeah, Earth can become like Venus, but here's the deal. We'll be long dead before that happens. So we have to apply brakes today, then we'll have it tomorrow, then we can apply whatever tomorrow tools we have. But we have to act like today is the last time. It's like sort today, enjoy tomorrow. So this was my presentation on basically nuclear fusion hulululu. I'm tired of it. Hopefully you have liked the video, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.